Okay, everybody, welcome to class. Happy Friday. Okay, let's start with the obvious. There's been a tragic accident. While trimming the stash, it had to go to blank slate. It was real bad. Sorry. Let no one say I wasn't committed to the stash. I gave a friggin' TED Talk with a big, ridiculous mustache. Yeah. I didn't spend enough because it got unruly, and that's why I was trying to trim it, and it got out of control. Should have left it to a professional. Sam. I find it strange that I'm fielding questions about this right now. It feels right. Okay, in other relevant news to this class, let's start with the learning objectives. Okay, we're going to start by defining the perovskite crystal structure. And the perovskite crystal structure is the raddest of them all. So if you liked all the other ones, just brace yourselves for this one because it's super rad. We'll talk a little bit about clays and carbon. Carbon's pretty interesting. We're going to introduce the 7 crystal systems, the 14 bravais lattices, which sounds like the title of a fantasy novel. We'll get to Miller indices. And then if we have time, we'll get to the coolest thing that you might learn from this whole class, which is X-ray diffraction. Okay, so let's dive right in. The perovskite crystal structure is different than all the ones that we've done so far because for the first time we've got multiple different cations. It can have 3 different ions in it. Okay, the other ones, things like sodium chloride, cesium chloride, those were binaries, mixtures of 2 atoms. This one can have 3. And so it offers just a huge amount of variety in terms of compounds that can exist in it. You've got 2 cation sites. We'll call them A and B. So let's call this the A site on the corner. The B site is in the center. And then you've got oxygen on the faces, right? So it looks kind of like FCC. You've got atoms on the corners and the faces. But in addition to what FCC would have, first off, it's different atoms. And second of all, you've got something filling this middle spot, okay? So when you look at the sizes of the cations that would occupy these sites, the A site is 12 coordinate, right? Starting by 1, 2, 3 times 8 divided by 2 ends up with the 12 coordination number. So 12 coordinate, is that a small atom or a big atom? 12 is ginormous, right? When we did our RC over RA ratio, that means that the cation is basically the same size as the anion. That's really big. So this is good. All of a sudden, we have a crystal structure that can accommodate a ginormous cation, but it also has a spot for a 6-coordinate cation, which is much smaller. So if your chemistry is such that you have a really big cation and a small one, you can put these things together, right? The ratio is 1 to 2 to 3. How do we know that? Well, we can count it up. You've got 8 times 1/8. That gives you 1 A atom. You've got 1 in the dead center. That's 1 B atom. But if you count the oxygens, there's 6 of them, and they're each centered halfway on a face, so 6 divided by 2 gives you 3. So it's AbO3. The AbO3, or sometimes they write it A1B1X3 is another type of saying the same exact thing. This is all the perovskite crystal structure. These things are incredibly important. We'll talk about them more when we get to chapter 12 because they're really interesting electronic materials. Piezoelectrics, ferroelectrics, almost all these things, magnetic materials. Tons of these are perovskites. Okay? Now, if your structure is what we call an ideal or a perfect perovskite, then it will be cubic, right? This length will be equal to that length and so forth. But if that will only happen if, think about the geometry requirement. This distance from here to here, that's root 2 of A divided by 2, right? So we could write out what that is. Root 2A divided by 2. What's that equal to in terms of radii? Root 2A over 2. Well, that's 1 radius of your A cation and 1 radius of your oxygen, right? Radius of A plus radius of oxygen. Everybody with me? I can see that because they connect along this face and it's halfway. But we could also calculate A in terms of the B, and the B and the oxygen, okay? And we would say that they connect from the bottom up this way, right along the body, right through the cube, right? So from the bottom halfway up, that's half of an A, right? That's A over 2. That should be equal to the radius of the B ion plus the radius of oxygen. Okay? In an ideal perovskite, when you plug in the values for your radii for B, O, and A, you would get the same A parameter. Right? That would be an ideal perovskite. But sometimes that's not going to happen, right? Maybe it's off a little bit, and so you end up with distortions, right? So the way that perovskite distortions manifest themselves is in tilting. So if this is the perfectly cubic version, you could take these octahedra, which are corner shared, right? They're sharing a corner as opposed to an edge or a whole face. They're sharing corners. And since they're corner shared, they're very susceptible to being able to tilt. We can bend them, right? See how this thing's tilted. What that does, it's tricky to see in this picture, but let's draw a two-dimensional version of it. Let's assume that our octahedra are not perfect octahedra. They're a little bit elongated. So I'm going to draw it. Right? A little bit elongated. And let's start putting these things together. All of a sudden, the ion that can fill the gap there, this makes it so a smaller ion can fit here and still be basically touching these things, which is what it wants to do to be stable. Okay? So this tilting accommodates even greater. So you already had a really flexible structure. It could fit a really big A ion, a really small B one, and now we can do even more because we can tilt these things. So it's a very versatile structure. And because of that, this thing is incredibly common in nature. You find the perovskite basically all over the place. It's very, very common. Okay? Sorry, that's not the A, that's the B. The A ion, not the B. Okay, you can calculate this tolerance factor, and it'll tell you how far from ideal it is by just plugging in these values, right? So T, our tolerance factor, is going to be equal to RA plus RO divided by root 2 times the quantity of RB plus RO. If it's perfect, that will equal 1. If it's not perfect, it's going to be a distorted perovskite, probably, okay? Which just means that there's some degree of tilting. It basically looks the exact same, it's just tilted a little bit. Okay? All right, let's talk about clays for a minute. Clays, silicates are the basis of most clays, and silicates are interesting. The building block of all silicates is this little tetrahedral unit, SiO4 4-, right? So you've got your silicon ion, and that's going to be Si4+, it's a cation. It's going to be surrounded by 4 oxygens, right? So you got your oxygens around it like that. And the net charge on that thing is 4-, right? It's got 4 oxygens. Oxygens are almost always 2-. So 4 times 2 gives you -8. And then you got the +4 silicon in the middle. So overall, that thing is still -4 charged, right? So to have this balanced, you're going to have to come up with extra positive charge somewhere. And the way that it can do that is pretty clever. It can do it by sharing sides, right? So for example, imagine this scenario. Let's say you've got this guy, but then we put another tetrahedral unit right next to it with silicon inside of it. Now, overall, what's the unit? Well, there's Si2, there's 2 silicons, but there's 1, 2, 3, 4, 5, 6, 7 oxygens, right? So now it got a little bit better. Now we've got +4 times 2. That's +8 to -14, okay? So that's sharing a corner, but they can also share an edge, or they could even potentially share a face, although that's less common, okay? So by putting things together, silicates together in different ways, you can form all these different structures, right? Going from the independent one, where it's alone, to sharing a single corner, to forming a chain where they form a continuous chain of these things. They can share them in planes, they can share faces. This is the basis of lots of the silicate minerals, and they're really complicated. Because there's all these different ways you can put these together, the types of minerals that silicates can form are really, really complex. We're not going to learn about them in this class. But silica is one of the most abundant elements in the crust of the earth, and so these things are everywhere. Any dish, basically, you eat out of probably has silica in it in some sort of funky arrangement like this. Now, clays are a specific type of silica. How clays work is they typically almost always have a layer of this silica, right? These things are put together in rings, just like we saw right here. You got these Si2O5 sheets like this. You have layers of that, and then connected to that, you almost always have an aluminum hydroxide layer, like this. So these aluminum, these are AlO6, right, octahedra, that are sharing, is that a corner, an edge, or a face? What does it look like they're sharing? They're sharing an edge. So this is an edge-shared aluminum hydroxide layer. These things put together, and now you have charge balance. This was a little bit of extra positive, this was a little bit negative, and overall, they're balanced. Or in other words, this little sheet's happy to just do its own thing. And then you've got what's called a van der Waals gap between these. A van der Waals gap, that's van der Waals bonding. What is van der Waals bonding? It's weak bonding. It's like a hydrogen bond, right? Since these are hydroxides, you basically get hydrogen bonding across here, which isn't very strong. Which is why when you take clay and you hydrate it, and you get it wet before it's been baked, right? All of a sudden you took something that was brittle. Anybody work with pottery? Any pottery heads in here? You add water to it, and all of a sudden you can make things out of it, right? You do that because you put water in here, these things slide apart a little bit, and they become ductile. The water makes it ductile because it allows things to slide past one another a little bit, okay? Which is pretty slick. It's pretty slick. No one's amazed by this. It's pretty slick. Once you get it wet, it's pretty slick. It's a good dad joke. Okay. Let's talk about carbon for a minute. Carbon's a great example to introduce a concept known as polymorphs, or allotrophy, or polytypes. These are all basically the same thing. Polymorph, poly means many, morph means structures. So many structures. If you have a compound that can exist in multiple different structures, you have a polymorph. Carbon's a great example. We've been talking about it all semester. Diamond and graphite are both pure carbon, right? And there's lots of different versions of carbon, right? This is diamond. What does this look like? This should look familiar. What compound does it look like that we talked about last class? It looks like zinc blende, except what? Yeah, instead of having two different, a cation and an anion, carbon is just carbon, so it's all the same. But remember, what do we know about carbon? It's a group 4 element, meaning it really wants to form 4 bonds, and then it's going to look like a noble gas and be happy. So if you look at all these things, it's bonded to 4 carbons everywhere, right? 1, 2, 3, 4 carbons are surrounding that guy right there. Now, we know that carbon can also exist as graphite, though, right? What does graphite look like? Josh, what's it look like? Hexagonal sheets. So let's draw our hexagons, right? It's like this. Now, if each one of these is a carbon, right, if that's a carbon right there, doesn't carbon have to have 4 bonds? What's happening? What's wrong? That's a nice sheet, but where's the 4 bonds? You have to start using double bonds to get there. Right? So you've got things like this, like make one of those a double bond. Now that guy's happy, right? And so you end up with these alternating double bonds going all the way through this, right? This gets tricky to draw. I'm jacking it up somewhere. Anyways, you guys get the idea. I'm messing it up. There's these alternating double bonds that go all the way through it. So that every carbon, if you add them up, it's got 4 bonds. Okay? So I guess it would be right here and so forth. Okay? So the same material, it's all carbon, but a different crystal structure. There's lots of materials that do that. Remember on the periodic tables, or not, the phase diagrams, I mean, when you would see something like, there'd be like this random like line, it would call this alpha, and this would be like alpha prime. That usually means it's just a phase transformation where it's similar to one another. So for example, the perovskite. You can have a nice cubic perovskite that we just showed you, or you can have the tilted one. That would be a good example of, they're both still perovskite, but they are technically different. So they call one alpha prime. That's typically what that means. It means the structure is pretty similar, but a small change happened. Going from graphite to diamond is not a small change. We call that a reconstructive transformation. A displacive transformation would be something like perovskite. If we go back up to perovskite, right here, going from this to that could be accomplished by displacement. You just have to move atoms a little bit. You don't have to break bonds. You don't have to rearrange it. So this would be a displacive transformation going between these two things. A reconstructive one is where you got to break bonds and just redo it. Okay? Carbon's interesting because it's got loads of different structures, right? You've got graphite, you've got diamond, but you've also got buckyballs, right? I don't know if these are actually good for anything, but they discovered them. I think scientists keep looking for things to do with these because they're just so cool, but I don't know if there is a great use for them. This is carbon 60. You take 60 carbon, put them together, you see hexagonal faces and pentagonal faces. It's like kind of like a soccer ball, right? Your buckyballs. Or like the geodesic domes, if anybody loves southern Utah and sees those goofy houses. Buckyballs. That's Buckminster Fuller invented that, right? You've got carbon nanotubes. These are very useful. Carbon nanotubes is another form of pure carbon. But this time, what do? You take graphite, just like this. You take this guy, and you roll it up, right? They take this end, and they connect it to that end, right? If you do that, all of a sudden you have graphite rolled up in a tube. Graphite is actually very strong in this layer. You've got graphene or graphite. It's very, very strong. You roll up in a tube, and now you've got a three-dimensional structure. Question?
So what determines the diameter of that tube? Or can it be different diameter?
Absolutely. Now, it's actually a little bit rare to have single-wall carbon nanotubes. If you see in the literature SWCNT, that's single-wall carbon nanotube. That means that a single layer of graphene was rolled up to make this tube. And it can be as big as you want. Let's say you want like a really big sheet of graphene, you get it to roll up, you're going to have a really big tube with some big diameter. There's lots of ways to control the diameter. If you take a nanotechnology class like Ling Zhang in our department teaches one, you learn all about the tricks of chemistry to make small tubes versus big tubes, versus single wall versus double wall or triple wall. You can do lots of cool different things with nanotubes. Why do we care about this? What do you use carbon nanotubes for? Are they good for anything? Fancy glass. You use them for fancy glass. What else are they good for? Medicine? Yeah, they do use them for medicine, for treatment. You can basically, if you've ever put, I forgot to I'll bring it next time. If you've ever put something in the microwave that is susceptible, it will heat up. Carbon is a pretty good susceptor. So for treating disease like cancer, they've tried to take things like carbon nanoparticles or carbon nanotubes and make them stick to cancer. Then they can microwave it, and your whole body heats up a little bit, but the microwave heats up this thing a heck of a lot, so it cooks the cancer. Does that sound crazy? That's actually what they do, which is wild, right? Now, there's lots of ways that you can make carbon nanotubes, not just the size or how many walls. You can cleave it on different angles. Let's say you cleave it right there, and then you roll it up, versus cleaving it along, say, that direction right there. Depending on the direction where you cleave it, you get radically different properties. One is a semiconductor, one is an insulator, one is a superconductor. Like bonkers different properties because you put it together and then nano effects, quantum confinement effects basically start taking over. So in the world of 2019 where we care about and we can all of a sudden do things at the nanoscale and see quantum effects, which is just when physics starts being weird because you confine things to small dimensions, these are a really cool playground, which is why there's tons of research on them. Now, even if you're not going to do that, if you're like, I just want to make a sweet mountain bike, just give me a job, you still should care about this, because these are, when you make them, they're incredibly strong and stiff. For example, they look like, here's a good example of this. They've got low density, but they are, where is it? They have a tensile strength of 50 to 200 gigapascals, which is nuts. It is the only material where if we wanted to make a space elevator, we could. And here's what a space elevator is. You put something heavy out in space, you drop a rope down, and you have something climb up the rope to get to space instead of launching a rocket. Any other material, the strongest steel, the strongest titanium, whatever you make it out of, Kevlar, any of these things would break under their own weight. But not carbon nanotubes. Carbon nanotubes are strong enough. The only problem is, what's the problem? What's the problem? Oh yeah, you mess up one little thing and your strength is not going to be what it is. What else is the problem with this? How easy do you think it is to make like a 3-mile-long carbon nanotube? Super trivial. Yeah, not easy at all. So we can make them, we're getting better at it. We can do, at first it was like nanometers, then it was like micrometers. They might be able to do it in the millimeter range now. We have a long ways to go. So we need smart people like yourselves to go and figure out how to make these things. Because already, even at those small scales, you can embed them in, say, epoxy and make a composite which has some carbon nanotubes, some epoxy, and you get sort of the best strength to weight ratio of anything out there, right? So they do this currently. They make bikes, they make tennis rackets, they make all sorts of things with carbon nanotubes inside. Now, you spend a fortune for them, but you get much better properties. Sam?
How thick would that tether have to be?
That's a great homework question. We could calculate it. We might. Okay. Let's move our conversation to crystal structures. To crystal systems. That was supposed to be crystal systems. Okay, crystal systems. We've talked about a couple so far. We've said that there's cubic and hexagonal. There's actually 7 different ones. If you look at it, here's how they are broken down. Cubic and hexagonal right here. Cubic's easy. All the angles between the different lattice sides are 90 degrees, and all the sides are equal length. Hexagonal is different. Hexagonal A is equal to B, so these two sides are the same, but they're not equal to C. The third one is a different length. And then these angles, 2 of them are 90 degrees and 1 is 120 degrees. That will give you the hexagonal crystal system. And then you've got all sorts of goofy other ones, right? Let's start with tetragonal. Tetragonal, A is equal to B is not equal to C. So these two are the same size, but that one's longer or shorter, okay? But all the angles are still 90 degrees, so it's still like a rectangle. It's just stretched out. It's like a cube that got stretched. How about this one? All 3 sides are different. That's orthorhombic, but it's still 90 degrees. And then you get to the horrible ones where they're not 90 degrees, like triclinic and monoclinic, where now the whole lattice is shifted by a little bit. And they exist. They get hard to work with, okay? Our minds are used to thinking in Cartesian coordinates, and it's a little bit of a stretch to say one axis is longer than the other, but we can handle that. It's much harder when you start tilting things, okay? So these are the 7 crystal systems: hexagonal, cubic, trigonal, tetragonal, orthorhombic, monoclinic, and triclinic. And then in those, you can center your atoms in different ways. For example, cubic, we've already seen these. Simple cubic, body-centered cubic, face-centered cubic. Hexagonal only has what's called simple, okay? Trigonal only has simple. Tetragonal, though, has simple and primitive, or they call it primitive or volume-centered. Those are the same thing. P or I are the same thing. They use different nomenclature because material science isn't hard enough. Okay, so if you add these up, 1, 2, 3, 4, 5, 6, 7, you add up to the 14. Okay, that's the 14 different bravais lattices. So of all the compounds that can form in all the tens of thousands of different crystal structures, if you look at them closely enough, you can say, oh, even though that thing's really nasty looking, it's really just this, but decorated with atoms in different ways. Okay? That's your crystal systems and bravais lattices. This is useful, and we'll come back to it when we get to X-ray diffraction. Okay. Something that we need to learn to do is talk about specific planes and directions in crystal lattices. Maybe there's a strength along a certain direction, and so you need to be able to describe, like, without pulling up the picture every time and saying, like, oh, it turns out that it's really strong along that direction as opposed to that direction. We need a way that everyone agrees is the same convention for talking about those 2 different directions. Or we can do the same thing with planes, like if we're talking about this plane right there along that face of this guy, as opposed to one that cuts through the middle of it or something, we need a convention. And the convention is Miller indices, okay? Here's how it works. Let's start with positions. When you're talking about a position, if you want to pinpoint a specific atom or point or an interstitial or whatever in the lattice, then it's round parentheses, UVW are the 3 values. Those are going to be between 0 and 1, so these are fractional coordinates, okay? So in other words, let's say you've got this tetragonal unit cell where A is equal to B is not equal to C, and I want to talk about this thing in the dead center. I would list it as 1/2, 1/2, 1/2, because it's half the way along this lattice, half the way along that one, and half the way up that big C one. Even though C is longer, this is still 1/2, 1/2, 1/2. Okay? What about right here? Well, we can just define our axes. You have to use the right-hand rule, so X, Y, Z. And what would be this point? 0 in the X direction, 1 in the Y, 0 in the Z. So it would be 0, 1, 0 with round brackets around it. That's points. Questions? That would be 0, 1, 0, round brackets. Everybody with me? That is a point. That's just like Cartesian coordinates. You guys did this in geometry as 9th graders or something. Right? Now let's do directions. Directions we're going to do, you're just going to take your final point minus your initial point. You're going to put it in square brackets, and you ditch the commas. Okay? So let's do this direction right here. What would that direction be? Going from that first point that we labeled to that new point, what would that be? Well, you just do final minus initial. Here's your final point. You're going to subtract the initial points. So you're going to take this u value and subtract that u value. Take the v, subtract v. W, subtract w. So let's do it. This direction would be, it's going to be 0 minus 1/2, so let's do minus 1/2. No comma. We're going to go to our next one, which is 1 minus 1/2, which is 1/2. Then we do 0 minus 1/2, which is minus 1/2. The next step is multiply or divide by some common factor until these are integers. So what are we going to do? Multiply it by 2. This becomes -1, 1, -1. Then one last thing is that it's common to write the negative on top like a little party hat. I didn't make any of these rules. That's just what they do. Okay? So the bar up top, if I say 1 bar, I'm saying -1. I don't know why they did this. This is what they do. Okay? Another way to look at this is if you look at that first point and you think to yourself, well, what's it doing? As it starts at that middle point and ends up here, you can just look at it visually and say, did we do this wrong? Final minus initial. Oh, what did we do wrong? What did we do wrong? No, that's not what we did wrong. Yeah. We chose a different origin. The first one, our origin was back here. So let's redo it. Let's fix it. Here, let's fix it. Let's define them both in terms of this origin. Right? You have to pick an origin and stick with it. Yeah, Jaden?
Is there any sort of standard origin that would...
I mean, I almost always pick this back corner, but I'll show you a reason why we can't do that always when we get to planes in just a second. This one's totally okay. You can pick that if you want. That's okay. So let's pick that one and let's redo that first point because we jacked it up. So what is that first point now? In the x direction, we need to go a half a unit cell back. In the y, we go positive half a unit cell. And this one, we're going to go positive. So it's going to, instead of being 1/2, 1/2, 1/2, it would be -1/2, 1/2, 1/2. So let's fix it. We broke it. Let's fix it. So 0 minus a -1/2 is 1/2. Positive 1/2. Now 1 minus 1/2 is 1/2. 0 minus 1/2 is -1/2. So it's basically the same as before. We just get rid of the little party hat on that one. Okay? Now it works. Now when you start here and get to this point, you had to come forward in the x direction. You had to go forward in the y direction, but you had to go down in the z direction. Okay? Everybody with me? Are there any questions on directions or points? Yeah.
So the left purple one is the vector with its dimension, and the right one is the direction.
Are you talking about these two things?
Yeah.
So this is like the intermediate step. This would technically be correct, but convention is if you ever have fractions, turn it into integer numbers. Now, we could figure out the length of this thing. The length is different than the direction. This is these are both pointing in the same direction, just one travels twice as far as that one. So this is not a measurement of length. This is just direction. That's why it's okay if it's integers versus halves. Okay? We can talk about families of equivalent directions. Let's draw this one. Makes a little more sense if I draw it. So let's draw a BCC lattice. BCC has atoms at the corners and one at the center. Now, the direction, if I were to draw a direction from this point to that point, cutting through the middle there, that is a fundamentally different direction than if I were to draw it pointing straight down. Because one intersects the middle atom and one only intersects along the side. But if I were to draw this one and this guy right here are the same. Well, they're not the same, but they're in the same family. They both intersect the same types of atoms. So if something's in the same family of directions, we have a special notation for that. We now use pointy brackets, right? And we'd say that these are all in the 100 family of directions. Why is it the 100? Well, what's the 100 direction? Where's 100? That means that, let's pick this back corner to be our origin for a minute. So we've got x, y, z. 1, 0, 0 means it doesn't go anywhere in the y or in the z. It just goes along the x. So in other words, that is the actual 1, 0, 0 direction. And these are all in the same family. But the one that cuts through the middle is different. What is that one? What is that direction? It starts out back here in this top corner. It comes forward in the x direction, forward in the y, but down in the z. So that one, this guy right here would be in the 1, 1, 1 family, which is the same as the 1, 1, 1 bar family. They're all the same family, right? They're the same family. It's a different direction, but they're all members of that same family that cuts through the body diagonal. Is everybody with me? Yep, question? A family means, good question. Let's say that we take this cube. We start out with this one. That's the actual 100 direction. And I'm telling you that it's the same as this one. What I mean by that is if you took this crystal, you grabbed it and you rotated it 90 degrees, this thing collapses to form that one. It's the same thing. Meaning its symmetry, the crystallographic symmetry, means that it's the same type of direction. It intersects along the same type of bonding. Does that make sense? Yeah. Other questions I can answer? Yeah. Yeah, that's a good way to think of it. Yeah. Okay. There are special rules for hexagonal crystal structures. Instead of using 3 Miller indices, U, V, and W, they use 4. And because we're just a little bit behind, we're going to skip this. So if that breaks anybody's heart, come to my office hours and I'll explain it in all its gory detail. I think there's a homework question where it asks it, so I'll probably remove that. So I've assigned the homework, but I think one of the book questions might ask for hexagonal. So watch for an announcement tonight. I'll probably just scrap that so that we don't waste time learning it. It's in the book. It's not that hard. I just want to teach it right now. So we're not going to. I won't test you on it. I'll drop the homework problem. Okay? More importantly, we need to talk about planes. Planes are harder, and planes are hard for students to grasp typically. But we have some sweet rules that make it really easy. Okay? So if you wanted to, we're not going to do any of these hexagonal ones. We're going to skip all the hexagonal ones. But these different cubic ones, how do you go about labeling these things? They're clearly different, so how do we label them? There's some rules. Here's the rules. Rule number 1. You pick an origin, right? If the plane passes through your origin, you have to pick a new origin or draw a parallel plane. Just pick a new origin, okay? So for example, if we picked our normal, let's draw one of these. Let's go to our BCC lattice again. If my pen decides to work, maybe. There it is. Okay, let's draw the BCC lattice again. Okay, we normally love to put our origin right back there. But what if our plane that we're trying to label is this plane right along there? Then we cannot use that origin. So we have 2 options. We can draw a parallel plane, like this one right here, right? You could rotate this cube, and that's the exact same plane, okay? Or we can pick a new origin. Either option is acceptable. Let's pick a new origin. Let's say, fine, we can't use that one, we'll put it right here. That's our new origin, right? So that is X, that is Y, that is Z. Okay? Done. Step 1 finished. Step 2, identify where the planes intersect the 3 axes. Okay? These axes, we know that they stretch to infinity in all the different directions. So your job is, where does this plane intersect those, right? So where does it intersect X? Does it intersect X? No, it runs parallel to it. So we would say that it intersects at, if we're doing X, Y, and Z up here, it intersects at infinity. At infinity, that's like by geometry where it would intersect it. Y, it intersects at -1. And Z, it also runs parallel to, so it's infinity. Okay? So step 2 complete. Step 3 says, take the reciprocals of these locations, and if it's infinity, when you take the reciprocal, it becomes 0. So this just becomes 0, -1, 0. Okay? Step 4, multiply by a common factor to get smallest integers. We already have an integer, so step 4 is done. Step 5, the integers, no commas, are placed in parentheses. Just like that. I don't put commas, or that would be a point. Since there are no commas, but there are round brackets, that means it's a plane. Okay? So this plane right here would be the 0, 1 bar, 0 plane. And you can put that little negative sign on top of it like a hat if you want to. It'd be the same thing. Okay? Let's do a harder one. We're going to follow the same 5 rules, but let's do it for this one right here. Okay. This time, let's make the plane do something goofy. Like, it's going to go like that. That's our plane. Okay? Chopping through our crystal. Let's pick our steps. Step 1 is pick an origin, and if your plane goes through your origin, pick a different origin. So, I don't know, this one's going to work nicely. Let's put it in this back corner where we usually like to put it. Okay? Now, where does it intersect x, y, and z? Remember, this is x, y, and z at that point, right? X, y, z. Where does it intersect x at? It intersects x, y, z at 1. Where does it intersect y at? It looks like either 3/4 or 2/3. Let's call it 3/4. I didn't draw it super amazing. What about the z? Yeah, that looks like a solid 1/2. So now what's the next step? Step 3 was to invert it. We take the reciprocal. So that becomes 1, 4/3, and 2. Step 4, multiply it so it's integers. What do we multiply by? Do 3. Math. 3, 4, 6. Put it in parentheses. You're done. That is the 3, 4, 6 plane. Okay? Any questions? 3, 4, 6. Yeah, question? If you multiply that one by 2, you still have a fraction. Then you have 8/3. Still a fraction. We want to get rid of the fractions. Yeah.
I'm confused about the first thing, why it doesn't intersect a y at 0. Why does it intersect a -1?
Okay, so this question typically comes up. In other words, if I chose my origin here, this is the same family of planes, right? This one we can't do, but we could label this one, and this plane in terms of this origin would be 0, 1, 0. The 0, 1, 0 and the 0, -1, 0 are in the same family of planes. You could rotate it. Also in that same family of planes would be this one up top here. Even though that is technically, if we use this as our origin, that would be the 0, 0, 1 plane. You could rotate it to make it any of those. They're all in the same family. They're all crystallographically identical. If you rotate that crystal, it would still be the same thing that you started with, right? That works here because it's cubic. If this was not cubic, if it was tetragonal where that was a longer c-axis, that doesn't work. They're not crystallographically identical. Okay? Let's do one more example. Oh yeah, Emma? That's convention. That's convention. That's how we do it. Now you can work this in reverse. Let's have you draw a funky plane, right? So here's our crystal. We're going to have you draw some weird plane. Let's do something really goofy, like -3, 2, 4. That plane, I'd like you to draw it. All right, well, what do? You work the steps in reverse. Instead, you start with step 5, which used to be multiply it by it so it's integers. Well, we already got integers, so we're great. So step 4 was, what was step 4? Take reciprocal. So let's flip it. This becomes -1/3, 1/2, 1/4. Next step back is look at where it intersects those lattices, the axes, excuse me. So in the x direction, it's going to go back in that x direction. So it's going to leave our cube if we keep that origin. So let's not keep that origin, right? Let's instead pick a new origin so it stays inside the cube. Let's pick one right here. Let's pick that as an origin for a minute, okay? I'll explain why we're allowed to do that in just one second. We're going to go back 1/3. Okay? 1/3 of the way back in the x direction. We're going to go forward 1/2 in the y direction. And we're going to go up 1/4 in that direction. And that is a horrible plane to draw. But it's that guy. Okay? Now, why are we allowed to do that? Just to arbitrarily move our origin like that? Yeah.
In reality, you have a bunch of cubes.
Bingo. In reality, you have a ton of cubes, and at any one of these points, you could draw that plane. And that's actually what happens. I think I've got a sweet illustration of that. Let's see if I can find it. Teaching 2019. Oh, no. Back to 2013. Grab Vesta. I think this is it. Yeah. At each one of your lattices, you could draw that plane. So these pink lines, those are those planes. So if you chose this bottom atom as your origin right there, this guy right here, let's make this bigger. So slow. Right? So if we chose that one right there, you could draw your first plane in terms of it. If this was the origin, then that can't be the plane that goes through it. That was our rule. But the first one could be here, and it goes up to there, right? I think this is the 1, 1, 1 plane. So there's that one. But if you chose this next one up, it would draw that next one, and so forth, right? Every one of these lattices you could draw a plane from. And so there's actually a whole bunch of these planes running through. And these will all have the exact same crystallographic symmetry. In other words, if I look at like the organization of the atoms on each of these planes, it's the exact same. It's the same exact organization of atoms. I hope you can see that there. Does that make sense? Okay? So it's not just, when you talk about the 100 plane, you're talking about a family of planes that run all the way through your lattice, not some specific one in some specific unit cell. It's all planes that are crystallographically identical to that. Okay? So you can go forwards or backwards pretty effortlessly. Are there questions about this? Yeah.
So you didn't divide by anything because you already had integers, but could you?
You could. Yeah, let's say that your what would be the right way to do this? So if I've given you something like this in integer format, you would never have to do that step. If I gave you something that wasn't, you could, though. If it was an integer, you can multiply. That's just, you'll never see that example, though, because they always report planes as whole numbers. So, yeah. What's that?
What if whole numbers happen to be double digits?
That's okay. You can do that. Like the 0010 plane, that exists. By the way, this gets confusing because now it looks like there's 4 numbers. So what do you do there? You put an extra space. Like when you're typing this, you put an extra space. Don't put a comma, don't put anything goofy like that. Just put an extra space there. Yeah.
So in terms of families of planes, and you said you can rotate the unit cell to find those families, is another way of saying that looking at the material from a different angle?
Yeah, like let's go back to this real quick. Let's pull up FCC 001. Okay? So here's the FCC cube, and we've drawn the 001 cells, right? I could rotate this whole thing around itself, and it's the same. Right? I can go all the way back around, and we start out right where we were. Okay? I could line it up this way, and I'd have to change my planes, but there's some running up and down here that are the exact same as well. All the sides of this cube are in the same family of planes. Meaning if we drew them, they would look identical. The atoms located on them are the exact same. Okay, we got 5 minutes. Let's sketch something. Okay, let's try sketching this. Another common thing I'll say is, all right, here's a plane. Sketch what the atoms would look like on that plane. So for BCC, I want you to sketch the 110 plane. So let's start by drawing what on earth the 110 plane is. So let's draw BCC versus FCC. You're going to get so good at drawing these. Okay, so here we've got BCC, we've got FCC. So let's place our atoms. BCC there at the corners and the body center. FCC there at the corners and faces, left, right, top, bottom, front, back. Okay? What would the 110 plane be? we're going to work our steps in reverse. 1, 1, 0. Let's start by flipping it. It's still just 1, 1. Now it's infinity. 1, 1, infinity. Okay? So now we just say, pick an origin. Let's try just picking this back corner. That's always my default, unless it doesn't work. So let's put our origin right there. 1, 1, infinity means it intersects the x at 1, the y at 1, but it never intersects the z-axis. So what is it? What does it look like? It's the diagonal through the cube body like that. That is our 1, 1, 1 0 direction, or plane. Wow. 1, 1, 0 plane. Everybody see that? It intersects x at 1, y at 1, but it never intersects z, so it's parallel to it. With me? Yeah, Faraz? So the last step in our Miller indices rules up here, well, I guess the last step was to multiply by an integer. The next one back was to flip it. We take the reciprocal, and 1 over 0 is infinity. Because math. Okay? So the next step is, now that we've sort of labeled it on here, I'd like you to lift that plane out and draw it for me. So we're going to draw it right here. So that plane is got a longer bottom length and a shorter height length. It's a rectangle. It's not a square, right? That plane looks like this for both of those, okay? It's longer on the bottom than it is tall. This length is your lattice parameter. It's a. But this is root 2 times a. This is a root 2 times a, okay? Now, where are atoms in these two scenarios? In this one, there's atoms at the corners, and there's one in the dead center that it chops through. It chops through these corner ones, and it chops through the one at the dead center. So let's draw it. We're going to try and draw it roughly to scale. If we draw this to scale, in body-centered cubic, they touch along that plane, right? So we would say there's an atom in the middle, and there's atoms doing this sort of thing. That would be a drawing of the 1, 1, 0 cross-section, right, of this unit cell. The atoms that are lying on this 1, 1, 0. How does FCC look different? Well, there's no atom in the center that it chops through. Instead, it chops through the ones on the corner plus these ones on the side where it's touching, right? So we could draw those. We'd say there's these atoms here. Like that. Right? It doesn't chop through any right here. Only on this face does it chop through that one. You guys with me? Why do we care about this? Because from this drawing, we can calculate planar and linear density. Or in other words, some planes are just more closely packed than others. You could calculate this. This has a total of 1, if you include the 4 times 1/4, plus 1 in the middle. So that's 2 atoms are centered on this plane, divided by some area. This one is the same thing. It's also 1/4 plus 2 times 1/2. So these happen to have the exact same planar density. But we could choose another plane where it has a different planar density, which is the number of atoms divided by the area of that plane. Isaac?
I assume that because of the way we set up unit cells, that these, if you were to do like expand on this, it would just be tessellated.
Yeah, absolutely. Yeah, because these are unit cells, you could just keep on drawing these, and you wouldn't end up with quarters of atoms. You'd get whole atoms if you did that. Okay, we'll pick up next time on a little bit more on planar density, and then we'll do X-ray diffraction on Monday.